Well, I have 6:01, and we'd like to just get started and hold this to an hour to get you to where you want to be within an hour. So if you're not already home, I hope you'll be headed there when we finish. So as I mentioned earlier, I'm Dave Cederberg. I'm the outreach coordinator for physics and astronomy at Purdue. With me tonight, or this evening, this afternoon, I have Professor Dimitrios Giannios, and Professor Giannios is going to be our content expert for the evening. And so I'm going to get us jump started with talking about Phyphox and a little bit about the experiment, and then we'll turn it over to Professor Giannios after we go through 3 or 4 slides. So I first of all want to just say thank you for being here. I also want to say thank you for what you do. These are difficult times. I mean, I taught high school for 20 years in easy times. And then, you know, I came to Purdue about 15 years ago and started a degree program. And since then, it seems like the more classroom teachers I talk to, the more it seems like it's going downhill in multiple ways. And I see the posts on Facebook and what some of you are dealing with. So you are heroes. Thank you very much for what you do. Thank you for being here. We're going to share the PowerPoint from Dimitrios's computer. I'm going to do the first few slides and then he will take over. But rather than waste time with both of us trying to share and unshare, we thought we would just run it from one computer. Let's go ahead to the first slide. A couple of points when we do this. I've done this in a classroom setting. I think it also presents an opportunity if you want to have kids do part of this at home. I mean, all they need is a tone generator and their mobile phone with the app. They could collect data at home if you think it might be difficult for you to do in a classroom setting. I have done this in a classroom where I just set the tone generator in the middle of the room and had kids collect their data, and everybody did it in real time. I will mention in the video, Daniel demonstrated this by taking his phone back and forth relative to the sound source. Keep in mind, you'd like to have the same speed or same velocity of your phone, both directions. Kids may or may not be quite that specific, but they're still going to get good results. I also have students do it in a circular motion where they will aim the microphone of their phone at the audio source and go around in an orbit. And that has some advantages too. You get the same data, but it also more closely, you know, if you're going to think about using the Doppler effect, for example, in searching for exoplanets or something in an orbital motion, it more closely models that. Obviously, extraneous noise is bad, and the slower the better. Last summer, we tried to do this with a car, and we probably worked for, in total, 3 or 4 hours, a couple of different times. We ran into 2 problems, one of which, you know, seems like a good idea. Why not go out to the parking lot, get a car, drive it back and forth? Car horns have 3 or sometimes 4 different frequencies. So if you're trying to find a frequency, you don't know which one to use. The other problem we ran into was we were going too fast. We were driving 20 or 25 miles an hour, and that's too fast. When you're doing your phone, you're going about maybe 1 meter per second. So if you want to try it with a car, you could use a trumpet, clarinet, musical instrument, or a tone generator on a loudspeaker, and you might be successful. We've not done that yet, but it could be worth a try. Dimitrios, next slide. Okay, so once you get your data, you're going to have to massage the graph a little bit. You're going to see 2 graphs when you look at the results, a velocity graph and the frequency graph. I don't really point out the velocity graph to kids because that's part of the lesson. I want them to calculate the velocity. But when you look at the frequency graph, hold your phone horizontally, stretch, and smoosh and slide to get 4 or 5 peaks that are fairly consistent and uniform. At first, it may not look pretty, but you can make it look a lot better with a little manipulation of the screen. We tried this with a basic frequency of 800 and moving at a reasonable rate of maybe 1 meter per second. We've got a difference of about 5 hertz. And so this is, we drew the red lines. They don't appear on the results, but your graph should look something about like this. Dimitrios, Phyphox will give you frequencies, which, you know, if you're studying sound, that's okay. But we'd like to transition to what we could do with the Doppler effect in space in terms of redshift. And of course, there's no sound in space, but astronomers are going to use wavelengths and not frequencies. So an interesting question I pose to my students is when we study sound, we don't really talk about the wavelength of a sound wave. So has anybody calculated the wavelength of a sound wave? I mean, an audible frequency? What would it be? Do you want to unmute yourself and just give me an approximate number?
We do the tuning fork lab over the tube into the container of water. And so for maybe a C256 tuning fork, we might have 20 centimeters of air that then we go on to calculate a wavelength with. It's an oldie, it's a goodie, it works, the kids like it, but that's how we get a wavelength of sound.
Sure. Cool. You know, when I taught chemistry, and we didn't do all that much with sound. But, you know, I think it's interesting. So you said 20 centimeters. So, you know, 20 centimeters, the wavelengths that we've used here in this experiment have been approximately ½ a meter. And so I think that's kind of a surprise to students that the sounds they're hearing, the frequencies are, you know, in the magnitude of something less than a meter, or as big as ½ a meter, which is even cooler. Anyway, when we did the experiment for the graph that I showed you previously, we had a base wavelength or a source frequency of 800 hertz. The measured frequency from the standpoint of the observer was 795 hertz. So I have 2 questions for you. If the observed frequency is 795 hertz, and we calculated the wavelengths for both of these. So I have a wavelength for 800 hertz of 0.425 and a wavelength of the 795 of 0.428. By either number, 795 or 0.428, it gives me a clue if I am approaching the source or moving away from the source. Now, this can be a little confusing for kids because you've got to switch your brain from wavelength and frequency. But am I moving away or am I moving toward the source with these numbers? Who can tell me? Anybody want to venture? Anybody want to venture being wrong?
Away. Wavelengths getting longer, so moving away.
Sure. Yeah, the wavelength is longer, so that tells me that I'm stretching out the wavelength. So yes, I'm moving away. Good answer. And so we can actually calculate the velocity of the phone with the equation that we have here. I'm going to multiply the speed of sound, CS, times the ratio, the difference between the observed minus the source, divided by the wavelength of the source. And we can put those numbers in. We get a velocity of the phone of 2.4 meters per second, which if you think about moving the phone back and forth, that sounds like a reasonable answer. Does anybody have a question up to this point?
Dave, just real quick. So when you're looking at this, the observed is, because I always think of it as the standard, what do you call it? The laboratory standard and the observed.
Yes.
Okay, so is the 800 the laboratory standard or is it the?
Yes, yeah, the
That's
800.
that's the laboratory standard.
Yes, that's a great question because number one, we can define right now, that's the laboratory standard. That's the frequency that's coming from your tone generator. So that's your standard. And the reason that's such a good question is because we're going to transition now from sound to light. And the laboratory standard that you refer to is going to be the light that's emitted from the source as compared to the light that we see as an observer. So, okay, everybody okay? I'm going to hand over to Dimitrios, and he's going to transition from sound to light.
So yes, when it comes to space, of course, there is no medium, no air for sound waves to propagate through, but light can make it through vacuum, can travel for billions of years, and that's how we see very distant objects in our universe. There is a very similar Doppler effect when it comes to electromagnetic radiation. Here we have again the expression, the formula for the Doppler effect for sound, and we have sub CS, the sound speed in this formula. A very similar expression is applied when it comes to light, and in that case we have the speed of light c. Of course, you all know that while the sound speed the speed of sound is quite fast, covers approximately 340 meters in 1 second, no one beats the light, which can travel 300,000 kilometers or 300 million meters in a single second. And I'm sure you have been telling to your students that light can rotate, go around the Earth several times in 1 second, or it can make it all the way to the moon in 1 second. Now, this Doppler formula here has lambdas, which are the wavelengths of the radiation of light. Lambda observed is, of course, the one that makes it, is the wavelength that makes it on the detector on Earth. And lambda source is the standard we discussed about, is the wavelength of the light at the source. This formula is very important in astrophysics because we can use it as a tool to measure velocities of different cosmic objects like a star, a planet, or a whole galaxy. Now, in analogy to the Doppler effect with respect to sound, there is something similar with for light. When the source is receding, when the source is moving away from us, then the wavelengths are stretched. The stretching of the wavelength at the detector means that the light turns to a more red color. Now, when the source is approaching towards us, towards Earth, then the wavelengths are squeezed. In that case, actually, we get shorter wavelength and higher frequency. In that case, we have a blue shift. When the source is going away from us, we have the receding source, we have the redshift. Now, speaking of redshift, you understand that there is this important quantity, the ratio of wavelengths, lambda observed minus lambda source divided by lambda source, which we call redshift. And that's an important quantity that if we measure, we can infer the velocity of the object, say the galaxy, with respect to Earth. Now, when redshift is positive, that means that the wavelength that the observer sees is longer than that of the source, and that means that the source is moving away from us. But how do we do this in practice? Well, here I have an example of how the light we receive, the spectrum of the light that we receive from a galaxy or a star may look like. You see the different colors, and indeed the galaxy has bright stars, hot stars, and cool stars with different colors. But on top of that, you see some dark lines. These are real lines. They are called absorption lines within the galaxy, and they have to do with the chemical composition, with the elements we have in these stars. Essentially, they are atomic transitions that they cut the light off at these specific frequencies. In this example, I show you these absorption lines as seen at a galaxy when we live inside this galaxy. For example, as we see the light from the stars in our own galaxy. Now, had this galaxy been moving away from us, all these lines or these dark spots would be shifting, all of them together and all of them towards the redder part of the spectrum. Now, notice here one-to-one correspondence between the lines. This line over here has shifted towards the redder part over there. This line in this example here, and I hope you can see my mouse moving.
Yes, we can see it.
Okay, so this line over there is moving towards the right, which is the redder part of the spectrum when the source is moving away from us. So by measuring the shift of these lines from where we would normally expect it and where we actually measure it, we can infer the redshift and therefore the velocity of the galaxy. Now, hopefully you are paying attention and you're not sleeping on me, so it's quiz time. So suppose you are the observers and you observe a dark line at a specific wavelength of 401.8 nanometers. Nanometers is a typical frequency that we measure optical light. So, okay, the line is observed at 401 nanometers, but we know that at its source, the resting wavelength is at 393 nanometers. Therefore, the observed wavelength is longer than the resting wavelength of the source. With this information, we can immediately answer the question whether the galaxy is approaching or receding from us. So what do you think?
It's receding.
It's moving away, right? The wavelength gets longer, the galaxy is moving away from us, and that's the cartoon I showed before. When the source moves away, the wavelengths get stretched. We have a redshift, not a blue shift. Not only this, but we can actually answer the question how fast the galaxy is receding away from us. In that case, we have to apply the Doppler formula. We have to calculate the velocity of the galaxy through this expression. C is the speed of light, and you may substitute this as 3 times 10 to the 8th meters per second. And substitute also in the formula the wavelengths. In fact, it may be a good point for you to use your calculators and calculate for me how fast is this galaxy moving away from us.
I have a somewhat off-topic question while we're calculating. If you look at a spectroscope or at the sun, why don't you get the absorption lines, or you get like a continuous emission lines? Like, why don't you just get mostly hydrogen and helium lines?
Right. Some of the important lines, of course, is hydrogen and helium. But then you do get traces, smaller amounts of heavier elements. So essentially what happens to the stars, they are really boiling. And that steering brings some of the heavier elements at very, very small abundances at the surface. So we do get also lines from heavier elements at the stars. But you are absolutely correct. Looking at the sun, especially at the surface of the sun, hydrogen is by far the most common element. If you want to.
So we have one answer in the chat, 6.48 times 10 to the 6.
Let's see, that sounds, let's reveal, let's put the numbers down. Let's work first with the wavelengths. here one trick is to realize that actually we can get rid of the 10 to the minus 9 meters. It simplifies the expression. So we really just need to take the difference of the numbers and divide with 393.3. And then we multiply with the speed of light. So I believe the answer is correct. It was, I guess, 6.48 times 10 to the 6 meters per second. Here I have it in different units. I have it as 6,480 kilometers per second. So it's a quite robust velocity. This galaxy is moving away from us at 1,000 of kilometers per second. That's actually fairly typical velocity, even a modest one. But literally, these objects are moving at thousands or tens of thousands of kilometers per second away from us.
Dimitrios, there's
Yes.
one more answer in the chat, and that is 0.02 C. Now, that's interesting, and I know you're going to come back to that speed of light here a little later, but I just wanted to point out that's one more way to express the answer.
Absolutely, that's a good point. And here at this line of the calculation, you see already that it's 0.0216 times the speed of light. So indeed, you can get your answer as a fraction of the speed of light. And in fact, the students may be asking this question. There are objects in the universe at the redshift, cosmological redshift of more than 1, at 2, 3, or 5. And if one naively applies this expression to this situation, he or she would get a speed larger than the speed of light, and that would be troublesome. The answer to this, it's a caveat, that this expression is applicable for velocities that are not approaching the speed of light. The non-relativistic, the classical Doppler effect of sound and the Doppler effect for light that we discussed here, this formula is applicable for speeds less than the speed of light. There is a relativistic expression appropriate for sources that are even further away. So if a student asks, is it possible to get faster than light? No, it's not, but this is not obvious in this formula. Keep that in mind. Now, with this tool, actually, we can study galaxies and we can study how different objects move towards us or away from us. After all, some 100 years ago, and it was just 100 years ago, astronomers realized that there are these islands of matter that are called galaxies. We live in our own galaxy of billions of stars, but there are billions and hundreds of billions of galaxies around them. And this is just a picture showing some of these galaxies in some direction in the sky. These are magnificent objects. Now, what Hubble did 100 years ago, or almost 100 years ago, is to use this Doppler technique to measure the velocity of these galaxies. In fact, he used two pieces of information. For each galaxy, he could measure the velocity in our line of sight, line of sight, as we say, meaning if they move towards us or away from us. But on top of this, he could also estimate the distance of these galaxies. That is done with other techniques that I'm not even discussing here. But it's measuring distance has been a big challenge in astrophysics for a long time. Now, he produced a plot where in the x-axis, he put the distance of the object and the y-axis, the velocity of the galaxy. And to his amazement, he figured out that all the velocities, or almost all the velocities, were positive, meaning that these objects are moving away from us. Not only that, but he also noticed that the larger the distance of these galaxies, the faster the recession, the faster the speed. So you see here this plot, its red point is a galaxy. Galaxies that are lying further away at large distance. The distance in astrophysics, we measure them in megaparsec, these strange units. But in any case, galaxies that are at large distance are also moving away from us at the largest, faster velocities. In these examples here are at 30,000 kilometers per second for the furthest away galaxy that we have in this plot. So what is happening there? We see galaxies moving away from us, and then the further away the galaxy, the fastest is moving. Are we, after all, in the center of the universe and everything is, for some reason, not liking us, moving away? Well, that's not quite true. What is happening in reality is a rather different picture where space and the universe as a whole is expanding. The classical example to show to the students is the loaf of bread baking, and it has inside the rising. Its rising is actually a galaxy. As the loaf is baking, it expands, and then the distance among all the risings is actually increasing. There is no center. It's just that the expansion of space, the expansion of the universe, results in everything is moving away from everything else. The further away to objects, the fastest they are also moving away from each other. Now, in this picture of the universe, in fact, when you look at red objects, you are also looking at objects that produced light long time ago, and now the light has been stretched to the redder wavelength. A galaxy that is very far away from us produced light, maybe a blue light billions of years ago, and has since this light wave has since propagated through the universe all these billions of years. And while the universe, the space itself expands, then the wavelength of the light expands together with space, and its color changes. It started from blue light, it evolved to yellow, and today that it arrives to us from this faraway galaxy, it looks red. So as the universe and space expands, the wavelengths get longer and longer. So that is in reality the origin of the redshift effect. You can make even a nice demonstration with balloons. As we can see here in the sketch, you can even put points, dots on the balloon that stand for galaxies. And by inflating the balloon, the distance among all these dots gets larger and larger just because space expands. Now, if we want to study faraway objects or light that came from the early evolution of our universe at early times in our universe, then we need, first of all, very big telescopes, because the light from these distant objects is very faint, it's very dilute. But we also need telescopes that look at the red part of the electromagnetic spectrum of the light, or even the infrared, further away from what our eyes can see. And in fact, a new era has begun for astrophysics. In December, there was the successful launching of the James Webb Space Telescope. This telescope has traveled in deep space at a distance 3 times the distance from the Earth to the Moon. It has gone far away, looking away from both the Sun and the Earth, so that it cools down. And it has expanded its mirrors. It looks like this. It's a huge combination of mirrors that goes 6.5 meters across and looks at the infrared part of the spectrum. So it's like the Hubble telescope on steroids. It's much more powerful. It looks at the infrared part of the spectrum. And thanks to its very large size, it can detect light from very faint sources. It can literally detect light from the very first stars that formed after the Big Bang, or the very first galaxies that ever formed. It can look also at other very faint objects, like low mass planets that are they're located around nearby stars. We can detect a planet that has the mass of the Earth, or even smaller, and around a nearby star, and we can try to find twins to our own solar system or to our own Sun-Earth system, and who knows, maybe we can look for life in these nearby systems. This era is just beginning. This telescope will be around hopefully for decades. We are hoping for a lot of discovery to take place. But I think I will stop here and we can open it to discussion.
When you, Dimitrios, when you say that with the James Webb, we will be able to see back into time to the first galaxies that were formed and the first stars that were formed, I almost can't comprehend that. So that's an astounding place to be right now. We look forward to that.
With Hubble, we had the big surprise back in the 90s. They sent this Hubble Space Telescope and looks at the optical, the visual part of the spectrum. And because it's in space, we don't have to worry about all these things related to the atmosphere. Going to space, you can observe much clearer view of the night sky, of course. And looking at specific location and direction in the sky, they expected, okay, we are going to see galaxies up to some cosmological redshift of 6, which means practically 1 billion years after the Big Bang, and then we don't expect to see many more galaxies. But staring at the location in the night sky for longer and longer, they figured out that there are galaxies that are fainter, further and further away. They could get galaxies out to a few million, hundreds of millions of years after the Big Bang at cosmological redshift of 20, meaning that the light that was produced from this object has stretched by 20 times until it makes it on Earth. The wavelength starts from some size L and it has made it to 20 times L when it makes it to Earth. And then we realized that the limitation is actually our detector. We are running out of light. These objects are so far away that even though they produce blue light, now it's transitioning into the infrared part of the spectrum, even beyond the red. So we need the detector that looks at the infrared and the detector that is very large so that we collect the light even from these very, very faint sources that are far away.
So we had a comment from the chat that hits that point exactly. The color of the galaxy, so galaxies that may have been bluish in the beginning are now reddish or even beyond the visible spectrum in infrared. So the point is the color of the galaxy depends on how far away it is.
Absolutely. And of course, always life is more complicated. Even a single, there are also red galaxies and blue galaxies. And that's another complication we have to take into account when we study these sources. Galaxies that have many young stars, they're more blue in color because young stars are the hottest stars and the more massive ones. Well, old galaxies turn red because they lose the massive young stars. But not taking into account, not thinking about these complications right now, that's absolutely correct, that galaxies that produce a lot of blue light very early in the evolution of the universe and far away from us. At this point, we cannot even see them anymore with our eyes, with optical telescopes. We have to go to the infrared part of the spectrum just to detect these galaxies.
When you think about seeing things that we've not been able to see before with the James Webb, we should be starting to, they're calibrating the mirrors now, trying to focus them all to a single point. And by later in the summer, we should be getting some images. What an exciting time to be alive. Who else has a comment or a question?
I am remembering from a long ago astronomy course, something about a throughout the universe microwave radiation. How does that memory tie into this? I don't know how to put my head back into that.
Well, it is related. This microwave radiation is everywhere. It is the leftover of the Big Bang, of the big explosion that set off the universe. Now, it's exactly the same effect if you think. Right now, we detect everywhere around us a very long wavelength radiation, very low temperature radiation, so low frequency and long wavelength. It's in fact, corresponds to a temperature of 3 Kelvin, 3 degrees above the absolute zero. So it's very, very long wavelengths. Now I'm embarrassed I don't remember by heart the wavelength. Anyway, the frequency is a few hundreds of gigahertz we are talking about. That's the characteristic frequency. You can use the formula with the speed of light to find the wavelength, some centimeters, I believe. The wavelength is literally centimeters of this radiation. And this is the leftover from the Big Bang. This radiation was initially at very short wavelength when it was produced at cosmological redshift of 1000, and has since stretched by a factor of 1000. And it has become centimeters wide. It's exactly the same effect has happened to what I'm talking about, the stretching of wavelengths of stars. But this radiation has been with us from the very explosion of the universe. It has undergone a huge amount of stretching.
I'm going to take you to the Google Drive folder where we have put some materials, but I also would entertain other questions if anybody has anything else.
And meanwhile, I can keep talking and, for instance, comment on a question that may be coming from students. Maybe some students have heard about the Andromeda galaxy, our nearby galaxy that comes and going to crash our own galaxy in some billions of years. Or that's the latest, at least, some of the latest information. So no reason for panic, but it's coming towards us. And that seems to contradict the whole story that we discuss about galaxies moving away from each other. So to be more accurate, indeed, when we are dealing with a nearby galaxy like Andromeda, or even the Magellanic clouds, which are dwarf galaxies, they are just captured and rotating around our own galaxy. At a smaller scale, you can see more like the random motion of galaxies, and the gravitational attraction of two galaxies can bring them together in a collision course. But at a larger distances, overall, the expansion of the universe takes over. So when we're looking at faraway galaxies, then they are all moving away from us and fast. So there are a few nearby galaxies in the local group, it's called, some 20 galaxies or so, that are moving rather randomly, and they feel the gravity of each other. So there are examples of galaxies that are close to us. They may even be moving towards us at this point.
So the problem that we gave you to calculate the velocity of the galaxy a little while ago is actually from the lesson. We have a few other questions in that lesson, one of which is data from the Andromeda galaxy. And so we are kind of slipping one over on our students when we have them go through the calculation, excuse me, have them go through the calculation of the receding galaxy. Then we have them do a second calculation where the velocity is negative instead of positive. And so when they arrange the equation and put in the observed frequency and the source frequency, they get a negative answer. And we do that purposefully just to shake them up a little bit, to give a point of discussion. Well, the first answer was positive. This one is negative. What does that mean? Well, by convention, if the galaxy has a positive velocity, it's moving away. And if it has a negative velocity, it's moving toward. So now we had one other thing come in on the chat. And here's a question, Dimitrios. Are the distant galaxies moving away from us, or are we moving away from them? Let's address that.
Yes, that's a good question, of course. And actually, probably the most correct way to think about this is really that the space among galaxies is expanding. So is like you inflate space and everything is moving away from everything else. Of course, from our point of view, we see the galaxies moving away. And if someone is in that galaxy over there and has his own telescope turned in our direction, or her telescope towards our direction, she will see actually that we are moving away with respect to this object. So velocity in some sense is always relative. We see things moving away with respect to us, right, or towards us. But how we think about this nowadays in astrophysics is really that space itself is expanding and then all the distances are increasing. If you ask me how we understand this at a deeper level, yeah, you shouldn't ask me because, right, it's kind of hard to wrap your head around it.
So let me ask a final question. From the theoretical astrophysicist's point of view, you know, if I'm teaching high school students, I might refer to the galaxies moving away from each other. Is that, in a theoretical sense, is that correct? Are the galaxies moving away from each other, or is it more really correct to say they're not moving away from each other, space is expanding? Or is it the same thing?
Yeah, I guess technically space is expanding is the more accurate way to describe. It's maybe gives the, if you say that galaxies are moving away from each other, then you could end up with question like, but where are they going? Are they going somewhere specific, moving away from each other? Well, when you blow the balloon and you put all these dots on the balloon and you think that you are living on the surface of a balloon, as the balloon expands, all the dots are getting more and more distant from each other. And of course, that's a simplistic view because in such an inflating balloon, we live on the two-dimensional surface of the balloon. And you can just see that as space expands, all the distance get larger and larger.
Okay, does anybody else have a question? We're almost out of time. We have a few minutes left. If anyone would like to chime in with something, we're all ears. Have any of you ever done with your students the balloon demo that Dimitrios is talking about? Okay, some of you have. Some of us like that. Some of us like the raisin bread model, where as the bread rises, the raisins move away. You know, they're just different ways of looking at the same thing.
Another one that I've done, I forget who puts it out, but there's a sheet that has a bunch of pictures of little galaxies on it. And then you make an overlay of what the universe looks like a second later, and you put it on top. And the only galaxy that you line up is your home galaxy, whichever one you chose as your home galaxy. And it shows how everything is, except your home galaxy, has moved and moved away, and that the farther the galaxy is, the bigger the arrow is. And
have you used this in your classroom?
Yes, it really seems to help the kids get the idea. And it also shows that there's no center to that expansion, because no matter what galaxy you choose, to that galaxy, it looks like they are the center, but that would be the same for every galaxy.
Yeah, it's an important message that there is no center to the universe, no preferred location. That should be made clear. Yes.
Okay.
That led me to think, is there a standard or a reference 000 point that you use to describe measurements from?
No. In fact, to write down the equations to describe the expansion of the universe, one of the principles that we use is that there is not such a thing. Everywhere, every single point can be a legitimate point of reference to study everything else. We call it homogeneous and isotropic. It doesn't matter where you go, the properties are the same. So there's no preferred corner in the universe. So that's how we build the whole model for the universe, by not having any preferred location.
The one thing that helped me with trying to get an idea about there not being a center or whatever is that I went to a professional development one year, and the astronomer that was working there had said, well, all the matter in the universe was all in the same place all at one time. So when the Big Bang happened, it wasn't like an explosion. It happened to all matter at the same time. So there's no center to that because all matter experienced the same thing at the same time. I don't know. It helped me try to wrap my brain around the idea of no center.
Jamie, the activity you referred to, if that's something you'd be willing to share with us, put it in the Google Drive that
Okay.
I'll send you the link to. Leonard, I would tell you the same thing. You had the rubber band demo, and I kind of know what that is, but if you have that in a form that's shareable and would like to put it in the drive, I'm sure everybody would enjoy it, and I know I would. So, and I would say any of you that have something you'd like to pop in the drive for other people to use, let's do that. And we can continue to support each other. I mean, my job is K-12 outreach. And so what I do is try and support teachers and faculty here at Purdue. So the more we can collaborate and work together, the better off we will all be. Thank you all for being here. I am at your beckon. If you have a lesson you're working on, want some feedback, want some ideas. I mean, I'm not an astrophysicist. I do a program called Saturday Morning Astrophysics at Purdue for students in grades 7 through 12. It's one of my favorite programs. I learn a lot, but I rely on people like Dimitrios and other faculty and grad students to provide the expertise. So thank you very much for being here. Go home if you're not, have dinner if you haven't, and stay in touch, and you'll hear from me again soon. All right?
Goodbye. Thank you.
Bye-bye. Dimitrios, thank you very much.